Welcome to Module 1.3, History of Artificial Intelligence. I am Dr. Alaa Jabbar Almaliki, and in this session for the Universiti Utara, Malaysia School of Computing, we will explore how we arrived at the current state of AI. You are likely familiar with modern tools like ChatGPT, but this chart illustrates the reality of AI development. For decades, progress was a slow, grinding flatline against severe hardware limitations before it finally erupts in the 2020s. Today, we will trace the chronological milestones of this timeline. We will analyze the systemic hardware failures that caused periods known as AI winters, and we will deconstruct the technological convergence driving today's generative AI. By the end of this lecture, you will step away from the perspective of an end user. You will begin analyzing these historical bottlenecks with the precision of a computer scientist. Ancient civilizations imagined artificial beings long before we had the technology to build them. The scientific discipline of artificial intelligence only became possible in the mid-20th century when engineers built the first room-sized digital mainframes. In 1943, Warren McCulloch and Walter Pitts proved that the biological firing of a neuron could be represented using mathematical equations with inputs, weights, and an output. This single mathematical model laid the foundation for modern neural networks. 7 years later, British mathematician Alan Turing published Computing Machinery and Intelligence, introducing a practical framework for evaluating machine intelligence. This diagram illustrates the Turing test. A human judge evaluates a human and a computer using text messages. If the judge cannot consistently identify the machine, the AI passes. Notice this tests a machine's ability to imitate conversation, not whether it understands language. The field received its official name at the 1956 Dartmouth conference, leading to rapid early success. By 1969, engineers built Shaky the robot, combining early computer vision, logical reasoning, and path planning to navigate physical rooms and avoid obstacles. These breakthroughs generated immense optimism. Researchers assumed human-level intelligence was achievable within a few decades, deeply underestimating the vast, unpredictable complexity of the physical world. That optimism met reality during the first AI winter, from 1974 to 1980. Early algorithms required vast amounts of data processing, but the computers of the time severely lacked the memory capacity and processor speeds needed to execute them. Funding collapsed. Interest rebounded in the 1980s with expert systems. These programs simulated human decision-making by relying on strict, rule-based logic. They followed rigid if X, then Y flowcharts to configure networks or diagnose medical conditions. But expert systems collapsed under their own weight. The hard-coded rules were expensive to develop, difficult to update, and machines lacked independent learning capacity. This led to the second AI winter. Pause the video here. Based on the historical bottlenecks we just covered, write down 3 specific technological requirements that needed to be invented to overcome these hardware and learning limitations. Progress continued in highly structured environments. In 1997, IBM's Deep Blue defeated chess champion Garry Kasparov. However, Deep Blue achieved this through massive brute force computational search algorithms, entirely devoid of general intelligence. By the late 1990s, the scientific community recognized a hard truth. Hand-coding explicit rules and relying on brute force computation were dead ends. They needed machines to learn independently. The solution arrived in the early 2000s. The expansion of the internet and cloud computing generated an explosion of digital storage, finally providing the vast, unprecedented datasets required to successfully train modern machine learning models. In 2012, a deep neural network called AlexNet won a major image recognition challenge by a wide margin. AlexNet proved complex neural networks could achieve exceptional accuracy when trained on enormous datasets using GPU parallel processing. This approach scaled rapidly. In 2016, DeepMind's AlphaGo defeated the world champion in Go. Because Go has vastly more possible board configurations than chess, this proved deep learning could navigate highly complex, intuitive decision-making environments. Modern large language models have shifted AI's role from labeling and sorting existing data to synthesizing novel text, images, and code. This transition relies on transformer architectures that can process trillions of data tokens to create original content. The current era of accelerated research began when the neural mathematical models of 1943 finally integrated with the vast datasets and hardware acceleration of the 21st century. We have traced a long path, from theoretical logic mapped in 1943 and the Turing test in 1950, through the severe memory limitations of the 1974 AI winter, to the deep learning breakthrough of 2012. The success of modern AI boils down to a specific structural formula: the convergence of massive big data, scalable cloud computing, GPU acceleration, and deep learning algorithms. As computer science students, you are inheriting this legacy. You have the advantage of working without the memory and processing bottlenecks that crippled the early pioneers. Use these historical architectural failures to anticipate and solve the engineering bottlenecks you will encounter in your future software research. I am Dr. Almaliki, and I will see you in the next module.